Brain-computer interfaces are devices that process brain activity and send signals to external software, allowing a user to control devices with their thoughts. With BCI technology, scientists envision a day when patients with paralysis, muscle atrophy, and other conditions could regain motor functions. Rehabilitation services could also adopt BCIs to accelerate recovery from injuries. Excitement around the possibilities of BCI has resulted in a thriving market, which is expected to triple in size from $2 billion in 2023 to $6.2 billion by the end of the decade. How do brain-computer interfaces work? Brain-computer interfaces are modeled after the electrophysiology of a brain's neural network. When we make a decision, or even think about making a decision, electrical chemical signals spark. This phenomenon is located in our nervous system, more specifically, in the gaps between neurons, known as synapses, as they communicate back and forth. Your brain is made up of millions of cells called neurons. These neurons work together in large networks to coordinate and control processes in your body, from understanding what you see, hear, smell, taste, and feel, to executing movements, to regulating your breathing, heart rate, and metabolism. Neurons communicate using electrochemical signals. When a neuron is activated, it generates an electrical signal that it can then transfer to the next neuron in the network, which will transfer it to the next, and so on. In this way, information can rapidly travel throughout the brain, connecting different areas that are responsible for different processes and body parts. In order to capture this brain activity, BCIs place electrodes proximal to these conversations. These sensors detect voltages, measuring the frequency and intensity of each spike as they fire or potentially fire. That information is then fed through local computer software, where it's translated in a process known as neural decoding. This is where a variety of machine learning algorithms and other artificial intelligence agents take over, converting complex datasets collected from brain activity into a programmable understanding of what the brain's intention might be. A brain-computer interface has three main parts. A device to measure brain activity. This is usually in the form of a headset, cap, or headband that has specialized sensors embedded in it to detect and record signals coming from the brain. A computer to process and analyze the recorded brain activity. The BCI software will try to interpret the user's desired action from the incoming brain activity, using specialized processing methods and algorithms. An application device to control. Once the computer has determined what the user wants to do, it will send a signal to the application device to carry out that command. For example, from our previous example, turning on a lamp. Invasive versus non-invasive BCIs. Invasive BCIs. BCIs directly connected to a patient's brain tissue and are implemented through surgical procedures. Because there are major risks that come with surgery, invasive BCIs are more appropriate for patients looking to recover from severe conditions like paralysis, injuries, and neuromuscular disorders. Non-invasive BCIs, BCIs that involve wearing a device with electrical sensors that serve as two-way communication channels between a patient's brain and a machine. They produce weaker signals since they're not directly connected to brain tissue. As a result, non-invasive BCIs would be better suited for purposes like virtual gaming, augmented reality, and guiding the actions of robots and other technologies. Applications of brain-computer interfaces. Robotic limbs and wheelchairs. By supplying a real-time neural feedback loop that rewires the brain, BCIs are capable of restoring movement, mobility, and autonomy for paralyzed and disabled patients, heightening their quality of life. In more chronic cases, robotic devices and limbs are integrated. Wireless headsets. Headsets are a way to deliver a non-invasive approach to brain-computer interfaces. Some boost productivity and enhance focus, as seen with Neurable's N10, while others restore motor functions to an individual's upper extremities following a stroke, such as the IPSI hand system by Neurolutions Inc. Spellers. Non-verbal individuals who may be stuck in a locked-in state following a stroke or severe injury can use eye movement for computer-augmented communication. Smartphone and smart home device interface. In several studies, users have exercised control of social networking apps, email administration, virtual assistants, and instant message services sans motor skills. Dimming the lights or changing the channel on a TV are examples of how BCIs can be adapted in the home. Drones. The Department of Defense has funded research to develop hands-free drones for military use. This would allow soldiers to telepathically control swarms of unmanned aerial vehicles. Examples of brain-computer interfaces. Neuralink's coin-sized brain chip. Neuralink, headed by Elon Musk, has developed a coin-sized surgical implant. In order to monitor brain activity as closely as possible, Neuralink's device, the Link, uses micron-scale wires of electrodes that fan out into the brain. Its primary focus is to treat paralysis. The company has inserted its implant in one patient and has plans to take on a second patient. Neurable's BCI enhanced headphones. Neurable is building headphones that interpret brain signals to level up productivity. Its first pair, N10, uses advanced data analysis and signal processing techniques to maximize a user's peak focus periods throughout the day. The company's MW75 Neuro builds on the N10, offering the same BCI capabilities coupled with more secure data encryption and a mobile app that makes it easier to analyze data-driven insights. Precision Neuroscience's electrode-packed film. Precision Neuroscience is approaching brain-computer interface systems with a surgically implanted brain chip that's minimally invasive and fully reversible. The Layer 7 cortical interface is a thin film of microelectrodes, about as thick as 1/5 of a human hair, that conforms to the brain's cortex just under the skull without damaging any tissue. In June 2023, Precision conducted an in-human clinical study of its neural implant. It has since expanded its research to include studies at Penn Medicine and Mount Sinai Health System. Synchron's endovascular alloy chip. Synchron is mapping the brain via blood vessels. Inserted through the jugular vein, the stentrode is a neuroprosthesis placed in the superior sagittal sinus near the motor cortex. The 8mm flexible alloy chip transmits neurological signals to a receiver unit implanted into the patient's chest, which then translates thoughts into clicks and keystrokes on a computer or mobile device in real time. Synchron is primed to start clinical trials and has teamed up with OpenAI to help paralyzed patients respond to text and chat messages. Challenges of brain-computer interfaces. Brain-computer interfaces have more than a half-century's worth of research and several proof of concepts that passed human trials. So what's the holdup? The two largest hurdles keeping BCIs from widespread adoption have to do with regulatory approval and funding. Given that brain-computer interfaces are registered as a sort of medical device, they lie under the jurisdiction of the FDA. That's all for this video. Hope you enjoyed today's content. If you think we have missed any important point, feel free to share your thoughts in the comment section below. Please like, share, subscribe and hit on the notification bell so you never miss any update. Thanks for watching.